Uh, are you able to see my screen?
Yes, but go full screen, Kuldeep.
Okay, screen.
We can see it.
Now is it
Yes.
visual?
Yeah, it is perfect. Go ahead.
Oh, so we are going to. I am going to present this quantum error correction techniques. This. So first we discuss introduction part of it. What is error correction? Then I will discuss classical errors. Then I will go on quantum error correction. Then I will discuss 3-qubit error correction, and in that I will discuss phase error correction, and then I will go further on 9-qubit source code. So this quantum computing is a significant breakthrough of this century. So quantum entanglement, quantum teleportation are the concrete stone that make quantum computing exponentially effective and fantastic. So the no cloning theorem provides strong confidence that quantum information cannot be cloned and replicated without detection. So this giving guarantee of that information will not be stolen. That is a very fantastic phenomenon. So people believe it, and that's why it's a very interesting field. So it's play a critical role in quantum cryptography and quantum communications, ensuring the security of quantum information transmissions. Theoretically, it is perfect, but in real quantum computers, we face some problems like decoherence, noise, error rates, imperfect hardware, etc. Because of that, quantum computing and this teleportation of quantum information, transmission of quantum information is uh, real life. It's see to very perfectly. It's little hard. So first we discuss what is classical errors. So in classical computing, information are represented using binary digits known as bits, which can be in one of two states, 0 and 1. When data is transmitted through classical communication channel, it can be exposed to environment factor and interference. So when we communicate the classical information due to environment, it faces some it interacts with the environment and information get erupted. So interaction with environment can cause the flip to bits to flip or change from their original values. Like if we transmitted 0, then it might be changes to 1. So if any value of information changes, then information being corrupted. These changes in the transmission data are referred to as errors. So these changing bits, they become the error of the information, and they can impact the accuracy and reliability of the information transmission. So what we do? So we have the problem. So now we need the solutions. So error correction techniques are employed in classical computing to detect and correct these errors, ensuring the integrity of the transmitted data. So how we correct it? So the basic idea of correcting the classical errors is we have a information. The information is expanded with extra information is expanded in with extra information during encoding of safeguard against error. So we what we do? We have a information. We make replicates of that. We increase information and then we transmit it. Technique like parity check and Hamming codes are used to introduce structured redundancy. During decoding, errors are detected and corrected. Like first, we made multiple copies of that in data. Then we transmit through uh, classical channels, and then we encoded with like copies. So we detect them, and detect errors, and then we correct it, and then we decode it. So after error correction, the original information is retrieved, ensuring data reliability in classical computers. Similarly, in quantum computing, we also have quantum errors. These errors are like some of these decoherence. So what is decoherence? It is the process in quantum mechanics where a quantum system loses its information, its coherence. Coherence means we have a state that is a superposition in superposition like 0 and 1. So decoherence means it's become in a one state like 0, either 0 or 1, resulting in that background of superposition and the emergence of classical like behavior due to interaction with its environment. So due to interaction with environment, it loses its coherence. So that is called decoherence. Some other errors are like gate errors. These errors can be caused by imperfection in the classical implementation of gate or external influence. Other kind of error is measurement errors. It Measurement errors arise from the fundamental principle of quantum mechanics, where the acts of measurement disturb the delicate superposition of quantum state, intro- introducing probabilistic uncertainty and influence the observed outcome unpredictably. So here is the comparison between classical errors and quantum errors. So type of errors we face in classical and quantums are: in classical we face bit flip error, but in quantum we face bit flip as well as phase errors. The source of these errors is in classical noise and Harvard effects, but in quantum decoherence, noise, gate error, measurement error are the main source of error. How we correct it? With in classical we make through redundancy we correct it. In quantum errors we have quantum error correction codes. We take help from that and then try to correct it. So first we discuss bit flip errors. So what is bit flip errors? Bit flip error in quantum computing occur when the state of qubit, which can represented by 0 or 1, is unintentionally flipped during the quantum operation. Like we have 0 and 1. So 0 become 1 or 1 become 0. So it's a bit flip error. Similarly, we have phase flip error. In phase flip error, it is a type of error that occurs when the phase of qubit is flipped, which means like we have a 0 state. During phase flip error, it become minus 0. So state 0 become minus 0 state. It is represented by Z gate. If a qubit is in a state, suppose psi, which is alpha 0 plus beta 1, where alpha and beta are complex number, represented the probability amplitude of the state 0 and 1. A phase flip error introduced a change such that the state become psi dash, which is equals to alpha 0 minus beta 1 state, without changing the probability of 0 and 1 state. So phase flip, what phase flip do? It's introduce the phase, but the probability of the state become same. It does not probability does not change during the phase flip errors, but it can change phase. So how to correct? So for that we have quantum error correction. So for 3-bit quantum error correction code, we have methods. So code. So we have code. We want to correct it. So we have to progress in steps. So we have one qubit. What we do is we encode it in 3 other qubits. Like make it 1 qubit, we make it in 3 qubit and try to correct it. So this 3-bit flip, this 3-bit flip code is correct 1-bit flip. So it encoded into 3 and it's only correct one error, single bit flip error. So this code has 4 components. First, we encode it, then we detect the error, then error, we have detected the error, now we will correct it. After correcting, we decode the our information and we'll get our original information. So let's understand the first encoding part. So we encode our 1 bit into 3 bit. So 0 is encoded into 0 state is encoded into 0 state and 1 is encoded into 1 state. So it's a 3-bit. Let's suppose we have an information psi that is represented as A 0 state plus B 1 state, which after encoding it will be psi equals to A 0 plus B 1 So let's discuss this how we do in on code. So first we have 0 state, we apply Hadamard gating, so it becomes 0 and 1. Is the superposition of 0 and 1. Now we apply CNOT gate on 0 and 1, and then we apply a CNOT gate on 0 and 2. So applying these gates, this 0 and 1 state will be become 1 bit information will be become 3-bit information. So now our second step is error detection. So let's suppose we introduced a error x. X means bit flip. So we introduced a error bit flip x on 0th qubit. Then we apply our detection techniques. So for that we introduce 2 more qubits. These are called ancillaries. So what we do, we attached our information with these ancillary qubits so that we can make the measurement. After measurement, we know that after measurement we lose our information, but here we introduce another information that will what that is it will do that it will measure that and our original encoded information will remain. So we measure here. So measuring during the measurement, we will detect the error that we have error in this 0th qubit and we will correct it. So how this correction happens? So if our our answer is detect 0 0 state, that means our information is correct. We don't have error. But if it detects 0 1 in measurement, then the state vector collapse into this 1 0 0 plus b 0 1 1. That means our original information has been changed. It has been flipped. Okay. So how we correct it? So our correction circuit, what it will do? It will change it to again 0 0 0 plus 1 1 1. If our answer is detect 1 0, it means then the state vector collapse in 0 1 0 and plus b 1 0 1. So what we do? We again correct it and get apply x get on second qubit and correct it. So it will become 0 0 0 plus 1 1 1. So these are the techniques in for one error in bit flip code. So now we will decode it. So we will apply C naught gate between 0 and 2, then 0 and 1, and then we measure it. So when we measure it, we get our results, which is 0 and 1 state. Originally we transmitted only 0 and 1 applying Hadamard gate, so which have 50-50 probability. Here we get this result also have errors because we didn't consider phase flip errors and also other errors we have. So let's discuss phase flip error correction. So in phase flip error is also a bit flip error, but in another state, like this plus plus and minus minus. So what is plus? Plus is a superposition of 0 and 1, and minus is superposition of 0 minus 1. So when we in our bit flip correction, we encoded our information in one bit into 3 bit. So we applied C naught gate on 0 on 1 and 0 and 2. So this is our encoding part. Then we apply 3 Hadamard gate. These 3 Hadamard gate converted 0 and 1 state into plus 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 and minus 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 states. So we converted our 0 1 state to plus minus state. Okay, so now our representation become in plus and minus. So in this space, in plus minus space, the phase flip error is a bit flip error. Suppose we apply x gate on plus, so it will become minus state, which is a0 minus b. So let's introduce a z flip error on on our encoded part. Then we will apply the similar techniques that we have been discussed in here in our error detection part. Similar technique we will use here, and then we again decode it and we will get our original results. So phase flip is just a bit flip error, but in different space. space like plus and minus. Now let's discuss 9-bit source code. So first, what we do? First, we encode using phase flip code, which become 0 into plus 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 and 1 in minus minus minus. So in this picture, you can see we have an information psi. We encoded it in 3-bit. Then we apply head market, 3 head market. So what it will do? It will encode our information 0 to plus plus and 1 to minus minus minus. So now we are in plus minus space. We were in 0 and 1 space. Now we are in plus and minus space. Now we encode using bit flip code. So in bit flip, what we do? We encode in 3 bits, 1 bit into 3 bits. So here what we do? We do plus we are in plus space. So plus will be encoded using 2 more bits into 3 bits. So plus become 0 0 0 plus 1 1 and minus will become 0 0 0 and 1 1 1. So what we will introduce this bit flip on every qubit. So we had 3 qubits, psi, 0 and 1. Now we introduce Hadamard gate. After every Hadamard gate, we will apply bit flip code. So it will become 3 to 9 bit. So our 0 will be transport. 0 will become some constant C, 0 0 0 1 1 plus 1 1 1. So now we have 3 copies, like so 0 0 0 1 1 1 0 0 0 1 1 1 0 0 0 1 1 1. So in bit flip we had 3 qubits. Now we have 9 qubits. So this 9-bit source code deal with bit error correction and phase error correction. So our 1 is converted into 0 0 0 minus 1 1 1 0 0 0 minus 1 1 1 and 0 0 0 minus 1 1. So this is source code looks like when we try to plot it. So we applied Hadamard gate on 0th qubit, and then we applied to NOT gate on 0 and 3rd qubit, 0th and 4th qubit, and then 0th and 6th qubit. Then we applied 3 Hadamard gate. So these 3 Hadamard gate, what will do? It will correct phase flip error. So it's become plus and minus space. So it converted it to 0 and 1 space to plus and minus space. Now we will introduce bit flip. We encode it in bit flip error correction technique. So we encoded 0th qubit into applied C naught 0 bit 0 and 1 and applied C naught in 0 and 2. Similarly, we did with third and fourth qubit and sixth and seventh and sixth and eighth. So this is our first encoding part. Now we will introduce some errors. So error X means bit flip error, and Z gate means it's a phase error. So we introduce this X and Z in our system. In our code, we introduce the error. Now we apply error correction techniques, and then we decode it. So similarly, we decode it in as just like we did in bitflip and faceflip, and we will get our results. So this is our results. We had applied head mark gate on 0th qubit, it will become 0 and 1. So 0 and 1 in the equal probability, that is 50-50. So we get this result. But this 9-bit source code only correct one error. So we get like this result. But we also have other errors also in like measurement error, gates error, and all this. Due to that, error is still in this. So 9 qubit bit source code is like correct. 1 qubit converted into 9 qubit to correct only one error, like one error phase and bit on only in 1 qubit. So we have more techniques like 7 qubit error correction code, 5 qubit error. We have more things like fault tolerance code, stabilizers code to detect the error and correcting it, that we developing. So, but this is it, theoretical results we have right now. But more techniques are developing, like, and our more advanced is stabilizers code, fault tolerance code are also to correct more and more. So we have more errors. So like, yeah, we introduce errors here in, but in real quantum computers, so error has been introduced. If your information is increased, your error also has been increased. So to detect that and all, you need more advanced techniques. So people are trying to develop that. So this is end of my talk. Thank you.
Thank you. Thank you, Kuldeep. Thank you very much. Are there any questions? Well, this was a very nice presentation, Kuldeep. Because it is coming toward the end of the semester, we will not include it for the exam, but it will be a good idea for everybody to go through this presentation once again. The recording will be uploaded at our Moodle resource. So please go through it again. And the 3-qubit, 9-qubit codes, correction codes are very important. Computers, quantum computers are very fragile, and most of the work, or a lot of work, is being done toward mitigating errors. You cannot avoid them. They are just there. And as Kuldeep pointed out, there are different kinds of errors. There are fundamental errors, the bit flip or the phase flip, and so on. And there are fundamental strategies which Kuldeep has discussed. So please go through it at your convenience. We can conclude today's engagement and stop the recording, Rahul.